All right. When you're studying thermodynamics as a process and study of reactions, these two events include, one, a change of energy, and two, a change in state of order. So in the nature of what a chemical reaction will do, it's a case of, is it rolling uphill or rolling downhill, is the way I like to present this. So you have two cases. If it's involving the change of energy, you apply the first law of thermodynamics. And the case of the second condition of a reaction is the second law of thermodynamics, and that for some reaction to occur, there has to be, regardless whether it's an endothermic overall or exothermic overall, some point in which it must roll downhill and take place. Now, in the world of thermodynamics, we have three possibilities for a reaction to take place. In case one here, if I put a sphere on the edge or a ball on the edge of an incline like this, an Earth's reference frame, and turn loose of the ball, it would, I think everybody would agree, it'd roll downhill. We don't have to do anything extra to make the ball move downhill. And in thermodynamics, this is called a spontaneous process. Or spontaneous reaction. If we have a level surface here and we place a sphere on that level surface and remove our hands from the sphere, it has no tendency to roll up or down or go left or right. We say that the reaction process is at equilibrium, and so we call that an equilibrium reaction. Now, if in the third case we put the sphere at the bottom of the hill and turned it loose, the probability of it rolling uphill on its own without any outside effort is zero. And this is a non-spontaneous process. A non-spontaneous reaction requires the input of energy or some outside effort in order to drive it. And this could be anything from heating the reactants, or applying electrical charge through the solution to initiate the reaction that depends on input of energy. There are both kinds of reactions, those that require input of energy and those that will take off as you mix them, and they will roll on their own. And then there's some that'll just lay there or will take place, but it'll be a dynamic equilibrium. Well, we've completed one part of this issue, and that's calculating delta H. Delta H, or the energy change for a reaction. Now, the second event that we need to take into account is, how do we take into account this concept of state of order? And that is the concept of entropy, E-N-T-R-O-P-A. and it's has a symbol S. Superscript means we're talking about entropies at 25 degrees and 1 atmosphere. So entropy, in its strictest definition, is a measure of the state of disorder. And so we're going to discuss everything in terms of disorder or change in orders moving to a more disordered condition. So you think in terms of disorder instead of order, kind of backwards mentally. So entropy to S individually is what we refer to as a measure of the state of order, scatter of something. Now that could take many different forms in terms of disorder. To illustrate what we're talking about in this is a positional entropy. And that's a certain disorder at 25 degrees. And it has a number with it. It relates to disorder. Now, the context of that, or the image that I need to give to you, can take many forms. And what I'm just going to do is show dots on the page. To understand positional entropy, we have to go to 0 degrees Kelvin and see what the entropy characteristic of a substance would be at 0 degrees Kelvin. Well, at 0 degrees Kelvin, there is no disorder. This is 0 disorder. Therefore, the positional entropy is, in fact, 0. There's no disorder there. So what I'm going to do is I'm going to place this as my image of disorder, order, whatever. Okay? Now, as I move away from this temperature-wise, and it picks up energy, the system, which is the little bars that we're talking about down here, becomes more disordered. That is, a temperature anywhere above 0. Well, we'll go to 1 degree Kelvin here. Okay? And what you would observe if you had an instrument that would see this order is this system would demonstrate a departure from the perfection of crystallinity. That is, you would move from perfect order to some degree of disorder. Okay? And as temperature continued to increase, you would see that, say, all the way up to 25 degrees Celsius, from 1 degree up to 273, 298 Kelvin, which is 25 degrees C. All right? And so the disorder in that context, I need another bar here. There. So you can see how the concept of disorder spreads the object out. The molecules move further apart and become more and more disorder. Now, we've already given 0 at perfect crystallinity, no disorder. As you move away, disorder increases. That is, the number that's presented to you is greater than 0. It's a positive number. Only if you have fragments of the element or substance will it be negative, because it's not in a neutral state. And we won't worry with that right now. So well, this is not its standard. I can take the zeros off of that. That's not standard. 0 Kelvin is not standard. 298 is. But you get up here, then you have S is a specific value. And represents, and if we're at 25, it is standard conditions. So scientists have calculated and determined what the standard entropies of a substance would be at 25 degrees. And so they published these numbers in the thermodynamic tables, and you see here, 25 or 298 Kelvin, and here we have an S. These are positional energy number, entropy, not energy, entropy of the various substances at 25 degrees, and they have a number there, okay? And they vary. Now, if it's an ion of some sort, disregard that. That's not part of what we're doing, okay? So entropy is always positive in what we're doing here because it's above crystallinity or above perfect order. And so anytime you look in one of the entropy numbers like electron 20, it doesn't matter what it means in terms of the number, it's just a higher than zero case of disorder. And so you go down through here and you see them, for the most part, except ions, it'll all be positive numbers, and that's associated with the positional entropy of that substance. Beryllium oxide has an entropy of 13.77. So what? Okay, but that is its number. Its thermodynamic property of disorder at 25 degrees. Okay, so this is what positional entropy means. But what are we talking about in terms of chemical reactions? When we look at entropy relative to chemical reactions, we compare the entropy of reactants to the entropy of products. So for any reaction, say reactants, go to products, then we have a state of order for reactions, reactants, and a state of order for the products. Now, two scenarios can exist. We establish, say, a positional entropy at standard conditions for the reactants. Okay, that's what the number, the measure of order, and then we have a positional entropy for the products. Okay, now if the reaction goes to more disorder, we'll find that the entropy of the reactants will be less than the entropy of the products. Okay? And the change in entropy, the standard of the reaction, is whatever the number you figured here for the products minus the entropy of the reactants. And in this case, as it goes to more disorder, this will be greater than zero or positive, meaning that the reaction is moving to a greater degree of disorder. Okay, and so that's the case where a reaction would go to a more disordered condition. An easy example, in my humble opinion, is the evaporation of water. If you have a liquid going to H2O as a gas, I think everyone would agree that the gas particles are more disordered. They're further apart. So you might have a condition where the gas particles are spread out over a long way, whereas in liquids, all the particles are very, very close together. And so this would be a high state of order, or let me do it a different way. I've got to speak in terms of disorder. So this would be a low state of disorder. And this would be a high state of disorder. So this is what we're ultimately calculating in terms of the disorder factor associated with reactions. And of course there is the other direction. Now one of the things I want to be sure to emphasize here, this is a change. This is positional. These are assigned numbers by some standard state. Okay? If we change the temperature and build a table, it would be different numbers, but they're still positional. So we have a positional entropy of the reactants, and we have a positional entropy of the products. And we take the difference and we come out with positive, or we can come out with negative. If it comes out negative, it's going to a less disordered state. Or this example, let's just take our positional entropies of the reactants and positional entropies of the products, which are numbers that are deal with each one, products and reactants. And assuming that the reactant entropy is greater than the product entropy, then the delta S, or the change in entropy, would be the S of the products minus the S of the reactants, and this would be a negative when you work out the numbers and put in the numbers. Okay? And a negative entropy, or negative change in entropy, I should say, is a less disordered condition. A compression reaction is inherently going to a less disordered condition. Regardless of whether it's gas or liquid or whatever changes. If that's gas, compression is going to, the molecules are coming closer together, which is more ordered. Whereas an expansion is the opposite. More disordered. Particles are moving further apart. And so this would be a plus delta S, expansion, increasing disorder, and the compression would be a negative delta S, or becoming less disordered. In the context of example, if I could, maybe I can get it in here without hiding everything. The 3H2 gas going plus N2 gas goes to 2NH3 gas, and you can see that that's a compression reaction. So the outcome of that, the entropy of that, that change in entropy of that reaction is going to a less disordered condition. And expand on that. We got 4 molar volumes going to 2 molar volumes. This is a compression, which means that the reaction or entropy change is less disordered. In the context of identifying that reaction in terms of entropies and scatter. Entropy equations are applied to the reaction, which means that what we're dealing with here is a change in entropy for a given process. So we're dealing with a changing of entropy, delta S, at standard conditions. So how can I change the order of something? Well, one is heated. I can add heat to a system, a bunch of particles, gas particles. They would move further apart, because when you heat a gas, it expands. Volume gets larger. We learned that from Charles' law. Increased temperature, increased volume. So when we talk about entropy change, this is proportional to input of energy, or delta H of reaction, enthalpy. So this is one factor that affects the degree of disorder. If you increase the enthalpy, have more heat going in, a more endothermic kind of thing, then you can expect a more scattered, more disordered issue. The next thing I'm about to write down kind of skews the brain a little bit, and it requires some explanation. Changes in entropy are also proportional to 1 over temperature. Now what that means is that's a positional temperature. And it means that changes in entropy are less observable at high temperatures than they are at very low temperatures. Okay? This is a positional temperature. Which means that if I were to consider the substance that we talked about earlier at 0 Kelvin, then you recall entropy is 0. The positional entropy is 0 in that case. Now if I increase this temperature to 1 degree Kelvin, entropy, of course, the degree of disorder will increase. We'll have a bigger number for it. And what you would see is this. Like that. Point here is that small changes at low temperatures, the observable change in order is easily visible. You can clearly define what the change is. You can clearly define that a change has taken place in the state of order. Okay? However, if we move to, say, 25 degrees in temperature and change it 1 degree. Okay, so here's our substance at 25 degrees. See, which is 298 Kelvin. And we change that by 1 degree to 26 degrees Celsius, which is, of course, 299 Kelvin. And what you would see is that if you looked at this first case at 25 degrees and then looked at the second case at 26, if I've done it right, can you tell that a significant change is taking place? No. So this is a small observable change. It's a small observable change at higher temperatures. And here you have a large observable change at very low temps, as in the close to zero kind of issue. And so that's about the size of why it is a reciprocal here relative to changes. Now all S positional entropies have a positive number. So that means starting at zero, they always increase from zero up to whatever temperature you want to do your work at. But in a change in entropy, it's a measure of how much it is observed in its disorder change. Okay? So delta S now is proportional to Q, directly proportional, and inversely proportional to the positional temperature that you are considering your reaction. So that's the entropy equation. Okay. In application of the entropy equation, you have both the first law and the second law involved in this expression. Q up here is your enthalpy, which is your heat of reaction. So we can put delta H of reaction here, and the temperature being, say, 298 or whatever you choose as denominator. Now, the application of this is to rearrange and solve for the delta H of reaction proportional to T delta S, like this. That's your application equation. What this implies is that you have three possibilities for this equation. And come down a little bit because I'm going to spread it out here. Delta H of reaction proportional to T delta S, like that, can do one of three things. For delta H relative to T delta S, you can have a calculation in a reaction such that the heat of reaction comes out greater than the T times the delta S. Or you can have the heat of reaction, standard conditions, equal to T delta S. Or you can have the heat of reaction less than T delta S. Now, what does these mean in terms of how you interpret the behavior of a reaction? Well, in my experience, I found it easier to make this interpretation. If I look at this delta H side and this T delta S side and call the one on delta H, the first law side, the order term. It's been very useful in turning this abstract into some reality of the equation. Over here on the T delta S side, we call it the disorder term. Right there. So, a long story short, listen to what I'm about to tell you in this. A reaction, whatever you choose, will either favor moving toward disorder, favor moving toward order, or remain at an equilibrium. And that's exactly what you are calculating. Whether it has a tendency toward order or disorder, primarily the number 1 and 2. The one in the middle is a condition for the reaction being at equilibrium. Now notice how delta H, the inequality, opens toward the delta H right there. That means if you make a calculation of H T delta S, and I'll show you how to do that, delta S, it's just a Hess's law thing, right here. If you come out with this, we say the reaction is non-spontaneous. if you calculate delta H and T delta S, the reaction's at equilibrium. And if the reaction calculation comes out with the disorder side, see the inequality? Opening toward the disorder side, that means the disorder is favored. The ball will roll downhill on its own. So this is a spontaneous process under those conditions, at those temperatures. Okay? So our job now is to calculate whether or not a reaction is spontaneous or non-spontaneous at the specified temperature we're looking at using this delta H proportional to T delta S. Okay, so essentially you are applying this, running out the T delta S and delta H times whatever temperature you're working at, and then you'll compare it to one of these three and say, oh, if I put A and B together, it's going by itself. Or if I add A and B, I'm going to have to heat it up, make it work. And I'll show you how to find out what the temperature is that'll make it work. Okay. Now, we want to calculate whether or not this reaction, the entropy number right here, is supposed to be 189 joules per Kelvin, which is 0.189 kilojoules per Kelvin. Right there. When you plug that one in down here, 189, you get a 0.119 kilojoules per Kelvin right there. Okay, and plugging it in here, we still get a non-spontaneous relationship, 44 for the order side and 35.5 for the disorder side. So 298.119 gives you 35.5. All right, now what the object was, and delta H is 44 and delta S is 0.119, then you calculate the temperature right there, and you put 44 over 0.119, and it comes out 370 Kelvin. Subtract 273, and it's 96.7 degrees Celsius. Sorry about that. Anyway, this is your called thermodynamic boiling point. Right there. So when everything's said and done, it's close enough to 100, so people use 100 degrees as the accepted boiling point of water. So that kind of, oh yeah, I see, it's kind of coming off the page.
So the critical temp is the same as the boiling?
No, the reason I made that note is closer to critical temperature. Now, it's not supposed to come out critical temperature.
Okay.
Like it's supposed to come out thermodynamic boiling point. 806. That's closer to critical temperature on a phase diagram. And I said, that's not correct. So that's why I went back and looked and found I'd picked up the wrong number off the table. That's what it's supposed to do. Okay, has everybody got the corrections in? I'm sorry about that. It happens. Anyway, moving along. Now, you can use the second law equation to determine spontaneity, non-spontaneity, or equilibrium conditions, but there is another equation that we have to look at, and it's called the Gibbs free energy concept or equation. Okay, make a note. Okay, Gibbs free energy, when we talk about that, is given as a delta G naught for a reaction like this. And the delta G value in thermodynamics is defined as the capacity to do work. The larger the delta G, the greater the intensity or capacity of the reaction that you're dealing with. Delta G is calculated in the same way as the delta S's and delta H's. In other words, delta G of a chemical reaction is the sum moles times delta G's of formation of the product minus the sum n dot delta G's formation of the reactant. So we'll apply the same thing as we did the delta H and the thermodynamics tables will give you a delta G value, as you see here, for all the odd and end equation compounds and substances that you can think of. And you add up the products, add up the reactants, take the difference, and you have a delta G. Well, what does delta G mean? It is also a indicator of all right. The delta G is a measure of spontaneity and comes from the entropy equation, delta S of reaction proportional to T delta S. Delta H of reaction, I'm sorry. Still hadn't gotten over pulling the wrong number out. Okay. Now, from here, you can have delta H, as we talked about earlier, greater than T delta S. You have delta H equal to T delta S, or delta H less than T delta S, in which the first case is non-spontaneous, second is equilibrium, and the third is a spontaneous, because the inequality opens toward and favors the inequality sign, the disorder term. Now, you can subtract T delta S from both sides of everything in here, and what you'll get is a delta H minus T delta S greater than 0. Then you'll have a delta S minus T delta S equal to 0. And this last one, you'll have a delta H minus T delta S greater than 0, like that. Delta H minus T delta S is, by definition, delta G of the reaction. So the simplicity of what I'm trying to show you is, if delta G is greater than 0, or delta G is equal to 0, or delta G is less than 0. Okay? And if delta G is greater than 0, we have non-spontaneous. If over here, and if we have equilibrium conditions, and you'll see this here. Okay, so what we're ultimately working toward is defining reactions in terms of Gibbs free energy, or delta G. Delta G is greater than 0 is non-spontaneous. Delta G equals 0 spontaneous. Equilibrium, or less than 0, it's spontaneous. Let's look at this one right here, and calculate spontaneity of this one. So actually, you start with the heats of formations of the components, and so we'll go look at delta G silver chloride. A minus 109.8, 109, 110, say a minus 110 kilojoules per mole, and times 1 mole, of course we have that right there. Now, delta G for the ion of silver solution, aqueous solution, 77 kilojoules per mole, or 77 kilojoules. positive. And the chloride is minus 131.3 and 131 kilojoules. Okay. And so calculating and determining whether this reaction is spontaneous, delta G of the reaction, sum n dot delta G is the formation of products minus sum n dot delta G formation of the reactants. So reactants and products. So the products are 77 plus a minus 131, and that's in kilojoules. Right there, minus reactants, which are a minus 110 kilojoules. Here, so that'd be 77 minus 131 plus 110 kilojoules. And so the delta G we get out of this, silver chloride is kind of a non-spontaneous process. And the issue is it does not deliver too many ions in solution, essentially. Okay, so the interpretation of the reactions can be related to what we call the delta G of the reactions, and of course we define spontaneity of that, either equilibrium, non-spontaneous, or spontaneous. If we talk about delta G of reaction that does not is greater than 0, or delta G of reaction less than 0, this is called a non-standard condition, is what the general characterization of it is. If delta G of a reaction is equal to 0, we say that whatever you're working on is at standard conditions. Now, this can be related to a little graphic diagram. I'll show you what we're getting to ultimately. Right here, a weird looking diagram like this. And then we go back to the rolling ball issue. If I put a ball here on this side of this curve, okay, we say it's in a non-spontaneous region, and we have to do something over here. So we get the ball moving, and what does it do? It rolls over here, probably somewhere up in there, okay? Now, it has a spontaneous to go back, and so it rolls back and forth until we get right here. These are no longer valuable. This is a condition called your equilibrium. Now, this curve is defined by an equation, delta G equals delta G naught plus RT ln of Q for reactions. Delta G of reaction without the little circle at it up here is the non-standard free energy. Okay? So you can actually calculate the free energy of a process, and we'll do this in electrochemistry more than we will here. Free energy of a process that's non-standard, and define whether it's spontaneous, not spontaneous, or at equilibrium under non-equilibrium conditions. Delta G of reaction naught is the standard equilibrium, standard conditions of the system. R is the gas constant, and is 8.314 joules per mole Kelvin. But when you use this, you'll probably use 0.008314 kilojoules per Kelvin, mole Kelvin. Because you want your delta G to come out in kilojoules. It's like a heat, an energy number. And T, of course, is temperature in Kelvin. Okay. Now, what's this all good for? Well, the Q value that was in here is compared to the K value. Okay, you recall that we could predict whether or not a reaction shifted left or right if we set up this Q expression, which is your products concentrations over reactant concentrations. Okay. But at equilibrium, delta G, well, if the system's in equilibrium, delta G of reaction is equal to delta G non-standard, let's put it that way. Delta G naught and plus RT ln of Q. If we're at equilibrium under standard conditions, this term goes to 0. That's the point. And so we saw this, what's left is delta G under standard conditions to equal minus RT ln of K equilibrium. So this equation, using thermodynamic values, allows us to determine the equilibrium constant for any reaction. That's what all the noise is about, as I went through this. So, of course, delta G, standard conditions, is delta H, Hess's law, minus T delta S, at whatever temperature you're working at, typically standard conditions. So you could calculate delta G for this position. R, again, is 0.008314 kilojoules per mole Kelvin, and T is standard temperature, if you're working at this, is 25 degrees C, 298 Kelvin. Okay, what kind of problems you got to worry with? Determine the equilibrium constant using thermodynamic properties of, say, the silver chloride dissolution. What's the equilibrium constant of that? Okay, so if you're given a silver chloride solid going to silver aqueous plus Cl minus aqueous right here, okay? And we know what the delta G of the formations are. Well, let me do that for each of these. I think I looked a while ago. We're looking at feathers. Okay. Okay, so we've got some numbers now, and so we want to apply this to this equation and determine what the equilibrium constant or solubility product constant is using data right out of the back of the book. We don't have to go to the lab and calculate it, everything we're going to do. Okay, so we found delta G formation for the reaction, excuse me, Rx, is, when we find out a while ago, well, I'll go ahead, minus 240 plus 77 minus plus 110. Okay, so we've got a delta G 56 kilojoules here, and R again is 0.008314 kilojoules per mole Kelvin, and we're going to do the temperature at standard, 25 degrees C, which is 298 Kelvin. And so to get the K value, delta G is equal to minus RT ln of K equilibrium constant at standard conditions. So this is 56 6 to equal a minus 0.008314, and temperature's 298, and ln of KEQ, ln of KEQ now is equal to a minus 0.008314 times 298 and 56. Okay, so now we can go KEQ as E to the minus 22.6. So that's 1.53 times 10 to the minus 10. So when we look up the equilibrium solubility product constant for silver chloride, if I can find it in there, can you see it? 1.8 times 10 to the minus 10 by the published value here, and we got 1.5 times 10 to the minus 10, which is close enough for government work, so to speak, and that's how you calculate use it to describe your reactions using thermodynamics. Take care. Take care, sir.
Doc, sorry, Doc. Is the lab still gonna be due Tuesday?
That's straight. It doesn't look straight to me because I bumped the. There it goes. This thing is the hardest thing on the planet to get straightened out. If I bump it, it goes crazy. Let's see if I got it right. Okay, I think I got it.
Nope.